All right, guys, welcome back. We're going to do 7-2 today, which is all about solving linear systems of equations by using the elimination method. So 7-1 was using substitution. 7-2 is going to be using elimination. Excuse me. So three objectives for today. The first one is we're going to use the method of elimination to solve systems of equations in two variables. Then we're going to look at how to graphically interpret the number of solutions of a system, right? So remember, if it's two lines, it can either have one solution, all solutions if the lines are stacked on top of each other, or no solutions if the lines never touch if they're parallel. Or if you have like a parabola in a line, it can cross once, it can cross twice, it can cross 0 times, things like that. So we're going to use the graph to determine how many solutions there are. And then we're going to use I'm going to have to write real small, systems of linear equations, still in two variables, to model and solve real world problems. So again, we're just focusing on two variables. 7.3 notes will be all about solving when you have three variables. Okay, so just a quick review on elimination. And this should be like, oh yeah, I remember this from Algebra 1. Solve the system using elimination method. So elimination method is when you add the two equations together to eliminate a variable. So you always want one of the variables to be the same coefficient, one positive, one negative. So in this case, it's already kind of set up for us, right? I have a positive 2y and a negative 2y, so I can just go ahead and add those equations together. The 2y's eliminate, and I'm left with 8x equals 12. After I add those equations together, divide both sides by 8, and I'm going to get x equals 1.5. Once I know what x is, I just pick one of these two equations and plug it back in. I'm going to use the top one just because they're all positives. So that kind of seems like maybe it's easier, but it doesn't matter. You'll get the same answer either way. So 3 times 1.5 plus 2y equals 4. 3 times 1.5 is 4.5 plus 2y equals 4. Right, we just keep solving, subtract. So I have 2y is equal to negative 0.5. Divide that by 2, and I get negative 0.25. It's okay that we have decimals. So that tells me that these two lines cross at the point 1.5, comma, negative 0.25. So if I were to graph these two lines, this is the point that they would cross. And so hopefully that's like super familiar, nothing too crazy here, right? Very rarely, I feel like, we get ones that are already set up for us. So we're going to look at, when you have to multiply one or both of the equations by a number. Just a quick review of that. I'm going to go through this very quickly. When we're using elimination, we need to make sure that both of our equations are in this form, where the x and the y are on the same side of the equal sign and your constant is on the other. You want to stack your x's, stack your y's, stack your constants. You'll have to multiply one, maybe both of the equations by numbers so that you get a coefficient that's positive and negative, so they eliminate. Then you add the equations and solve. So here, when I'm looking, I see I have a 5x and a 2x. So if I want to eliminate the x's, the smallest number I can get to is 10. So I could do 10 and negative 10, and that's fine. Or I have 3 and negative 4, and the common number there is 12. So I would have to multiply by 4 and 3. And it doesn't matter which one you do. You can eliminate the x's if you choose, or you can eliminate the y's if you choose. I kind of like the y's just because one's positive already and one's negative already, so it kind of like works in my head. So I'm going to multiply this whole top equation by 4, and that'll make this a 12y. And I'm going to multiply the whole bottom equation by 3, and that'll make this a negative 12y. So 4 times 5x is 20x plus 12y. Common mistake is people forget to multiply the 4 by the 9 as well. Okay, so 4 times 9 is 36. So you have to make sure that you multiply every single term. 3 times 2x is 6x. Then I have a negative 12y, and 3 times 14 is 42. So now I have a variable that's going to eliminate, so I can add those equations together. The y's go away, and I get 26x is equal to 78. Divide both sides by 26, and I get x equals 3. Now, once I have both x solved for, I'm going to plug it back into one of my original equations. And again, it doesn't matter which one. I'm just going to use the top one because it's all positives. But it doesn't matter. Okay, x is 3, so I have 5 times 3 plus 3y equals 9. So 15 plus 3y equals 9. I'm just going to keep solving. Get 3y is equal to negative 6, so y is negative 2. So if I were to graph these two lines, they would cross at the point 3, negative 2. My dog has decided that this is a good time to start using the squeaky toy. Okay, so these two lines cross once at the point 3, negative 2. Let's look at another one. What happens if you get no solution? So let's look here. So I have x's, and I could get, maybe multiply this one by 2. If I multiply this by 2, it would eliminate with this guy. So I kind of like that. It seems like a quick and easy way to go because then I only have to multiply one of the equations. The top equation becomes 2x minus 4y equals 6. And the bottom equation becomes negative 2x plus 4y equals 1. So when I add these together, my x's eliminate and my y's eliminate. So I have 0 on that side. And then on the right side, I have 7. And then you are like, what the heck just happened, right? Because 0 does not equal 7. So that means that there is no solution. Now, if we think about the solution is the point where the two graphs cross, right? So I have two lines, and where they cross is the solution. If there's no solution, that means that they don't cross. And so lines that don't cross are parallel, right? So that means that these two lines are parallel. We draw parallel lines with those little arrows. And in case you can't tell about my terrible artistic ability, we can label them as parallel lines. Okay, so anytime you have no solution, the solution is where they cross. If there's no solution, they don't cross. So they must be parallel. All right. So now, hopefully that's review. We feel good about that. That's nothing new. We are going to look at what does it mean, like I just said, right, when there's one solution or no solution or infinitely many solutions. So we're going to look at how do I interpret the solution from the graph. So it says for a system of two linear equations in two variables, the number of solutions is one of the following. A system of linear equations is consistent if it has at least one solution. Okay, so either infinitely many solutions or one solution. It's consistent. And it's inconsistent if it has no solution. Okay, systems are equivalent if they have the same solution. So let's look at this. If there is exactly, I'm gonna scroll down actually, so I can draw it as we do it. Okay. If there's exactly one solution, it means that the lines cross at one point. So when you solve, you'll get solve, you'll get x equals a number and y equals a number, and then you'll put it together as a coordinate point. Okay, so if you have exactly one solution, it means that you'll have a line. That was a pretty incredible line. And you'll have another line, right? And it will cross at one point. And that one point is your solution, and your answer will be an xy coordinate. If there are no solutions, the solution is where they cross. If there's no solution, they don't cross. So that means that they're parallel. So if there's none, right, you get parallel lines like so. And then you'll get something weird like what we got 0 equals 7, right? You'll get something and you'll get a false statement like 0 equals 5 or something like that. So I guess here we can put like x equals and y equals, right? You're going to get x and y's. Here you're going to get a false statement, something that is not true. 7 equals 12. -4 equals 8. Whatever it is, if it's a false statement, that means that there's no solution. And if there's no solution, the lines are parallel. If there's infinitely many solutions, which is the last option, infinitely many solutions, that means that those two lines cross infinitely many times at every single point. So that means you have a line, right? And then you have another line that's right over the top of it. So I'll try to draw them. The two lines are identical. They're the same line. And so what that does is you'll solve, and you'll get something that's a true statement. Like 3 equals 3, or 12 equals 12, or 4 equals 4, or whatever it is. 0 equals 0. And so then we write something like all real solutions. And it's important that we write that word real, right? Because we're not dealing with imaginary numbers here. We're only looking at real numbers. So we can write all real solutions, or we can write infinitely many solutions. And that's either one of those answers is fine. So again, hopefully this news isn't new, right? It's just a nice little review of the answers that we usually see. So let's we've looked at one solution, we've looked at no solutions, so now we're going to look at infinitely many solutions. So again here, I kind of like the x's because all I have to do is multiply by -2. So let's just do that. So that gets me -4x plus 2y equals -2. And then I have 4x minus 2y equals 2. And if I add those together, I get 0 on the left and 0 on the right, which is a true statement, right? 0 does equal 0. So this means that it's all real solutions. All real solutions. Or you can write infinitely many solutions. Either way, either one. You don't have to write both. Please don't write both. Just write whichever one sticks out to you and screams, "This is what I want." So again, hopefully these are not scary or anything like that. We're going to look at a couple little bit more difficult ones, and I'm just going to show you kind of some tricks on how we can make them look a little less scary. So the first one is, what if you have all decimals? Like, right? Gross. I don't want decimals. I hate dealing with decimals, even as a teacher. Like, for some reason, it just makes it look more complicated. So the trick is to look at each of your decimals and see how many places do I have to move all of these decimals in order for them to no longer be decimals? So like here, and you don't have to write this part, I'm just going to show you, right? So I move the decimal place twice, it becomes a 2. Here I move the decimal place twice, 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 right? So all of them are twice, which is kind of nice because I don't have to worry about like multiplying all of them by a, if one of them was 3 times, I'd have to multiply them all by a bigger number. So we can multiply by 100. Why did I pick 100? Because I'm moving the decimal place twice. If I only had to move the decimal place once on all of these, I would multiply by 10. If I only had to move had to move the decimal place 3 times on even one of them, I would multiply by 1,000. Okay, but in this case, since it's all 2 decimal places, I'm going to multiply by 100 to clear decimals. Right? So if it was like 1 decimal place, I would multiply by 10. If it was 2 decimal places, I would multiply by 100. If it was 3 decimal places, I would multiply by 1,000 or whatever, right? So in this case, because they're all 2, I get to go through and I can multiply the whole equation by 100. And it does not change the solution at all. It just changes what it looks like. So 100 times 0.02x is just 2x. That gives me minus 5y equals negative 38. I like those numbers a lot better. Here I have 3x plus 4y equals 104. I'm very much more happy with those numbers. Now now I need to eliminate a variable. Do I want to eliminate the x's or the y's? I'm going to go with the y's just because one's negative and one's positive already, but the x's might produce smaller numbers. So really it's whatever you prefer. Okay, so I'm going to multiply this top equation by 4, which is okay, and the bottom equation by 5. So this gets me 8x minus 20y equals negative 152. And then 15x plus 20y equals 520. Now I can go ahead and add these equations together. These guys cancel. 8 and 15 is 23, so 23x. 520 minus 152 is 368. Divide both sides by 23, and I get x equals 16. Awesome. Now, I don't really want to plug in x equals 16 into these decimals. Like, I can, but I don't really want to. So I'm going to pick this top equation, and I'm going to plug in my 16 into that top equation. So 2 times 16 minus 5y. At this point, we should feel pretty comfortable solving with elimination, right? Just using these kind of helpful hints to help us along the way. I'm going to subtract 32 to the other side, and I get negative 5y equals negative 70, and so y is equal to 14. So these two graphs, even though they have all these crazy decimals, if I were to graph them, they would cross at the point 16, 14. So there's one solution. These graphs only cross at one point, and that one point is 16, 14. So hopefully that kind of makes sense how we got rid of all of those decimals to kind of help us through it, make it a little bit easier just to look at and work with. What if you have fractions, right? Gross. Fractions are so scary. Just kidding, they're not that bad, you guys. What I would do is I would look at, and again, I wouldn't write this on your paper, but just for me to show you, I would look at the denominators here. I have a 2 and a 5. So like common denominator, the least common denominator between 2 and 5 is 10, right? So let's make a note. I would multiply by the least common denominator. Maybe I'll write it out since we seem to not remember sometimes what LCD is. The least common denominator to clear the fractions. So what that is going to do, right, I'm allowed to multiply everything in one equation by a number. So here my LCD is 10. So I'm going to multiply this whole top equation by 10. Right? So maybe we'll kind of do this off to the side. 10 times 3 over 2x. Well, if it's 10 over 1, excuse me, right, I get 30 over 2, which is 15, so 15x. So this is going to get me 15x. And then 10 times negative 1/5 y. I have 10 over 1, which is 10 over 5, which is 2, and then there's the negative, so it's negative 2y, minus 2y. And then 10 times 8 is 80. So by multiplying by 10, I've gotten rid of the fractions. Now I can go ahead and do the bottom equation, which doesn't have fractions. And now I'm ready to just solve like normal. I really like the y's just because the numbers are going to be smaller. So let's get negative 2 and 3 to negative 6 and 6. So I'm going to multiply this top equation by 3 and the bottom equation by 2. So 15 times 3 is 45 minus 6y. And 3 times 80 is 240. 2 times negative 2x is negative 4x. Plus 6y equals 6. And we are cruising from here. 6's eliminate. 45 minus 4 is 41x. And 240 plus 6 is 246. Divide both sides, and I get x equals 6. And then I like this bottom equation just because it's simpler, right? So negative 2x plus 3y equals 3. X is 6. It seems like we've kind of solved for x first on all of these. That's not always the case. You don't always have to solve for x first. Plus 3y equals 3. So I have negative 12 plus 3y equals 3. Add 12 to both sides. 3y is equal to 15. And so y is equal to 5. So again, these two lines cross at the point 6, 5. So there's one solution. And the solution is 6, 5. So hopefully they're like, oh yeah, this is super easy. I love this section. Woohoo! We just have one objective left, which is awesome. And it is, using our linear equations to help us on real world problems here. So this question says, there are two main questions, or I guess not the question, but the objective. There are two main questions to ask if you are deciding if a system of linear equations is the appropriate method for solving an application. The first thing is, does the problem involve more than one unknown? Right? And then the second question is, are there two or more equations or conditions to be satisfied? So if one or both of the above conditions are met, it is appropriate to use systems of equations to solve. Right? So if you're looking at so for the first question, if you want to know like the number of what was the example that we did in 7-1? The investment, right? How much money was invested at 9%? How much money was invested at 11%? That is two different unknowns. So that would be your clue to use systems of equations. The other part, B, if there's two or more equations or conditions to be satisfied. If you're given like a quantity of something, right? This and this added to like the number of adults going to the movies and the number of children going to the movies total is 31 people. That's an equation. And then you can say an adult ticket to the movies costs $5.50, a kid's ticket to the movies costs $2.50, and they spent a total of $70. That is another equation. So those are kind of the helpful hints in figuring out whether or not you want to use a system of equations. So here, let's look. We're going to kind of have to write kind of small here, so that's your warning. It says an airplane flying into a headwind travels the 2,000-mile flight distance between Cleveland, Ohio, and Fresno, California in 4 hours and 24 minutes. On the return flight, the same distance is traveled in 4 hours. Find the airspeed of the plane and the speed of the wind. Assume that both remain constant. So I want to know how fast is the plane going, and then how fast is the wind going against the plane or with the plane. So the first thing that I see is that here I have time in hours. Here I have time in hours and minutes. That's no good for me. I need that only in hours. So I know that it's a total of 4 hours, and I know that it's 24 minutes out of 60 minutes. So if I do the math here and get a common denominator and add it together and blah, 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 I get 4.4 hours. So I cannot use a time that's hours and minutes. It has to all be hours. So that's Q1. Okay. So there's two things that it's asking me to find. The airspeed of the plane, which I'm going to call A, and then the speed of the wind, which I'm going to call W, wind. So airspeed is A, and then wind is W. So let's look. It obviously took more time to go from Cleveland to Fresno. So on the way there, the airspeed of the plane was going against the wind, right? So the wind was slowing the plane down. So hopefully that makes sense. Okay. And then on the way back, the airspeed of the plane was going with the wind. So it was helping it go faster, right? So this tells me that here it's the airspeed of the plane minus W is one equation. And let's just leave it because we'll need to figure out we know that it's 4.4 hours, but we don't know miles per hour because I want speed of the plane and speed of the wind. So we'll just look at that in a second. So that's the way to Fresno. And then the way back from Fresno, the wind was going with the air. So you're adding those together. So let's look at how we can come up with that. Okay, so let's go from Cleveland to Fresno. I know that it was 2,000 miles in 4.4 hours, right? Miles per hour. But I don't want 2,000 miles per hour. I don't want 2,000 miles per 4.4 hours. I want this to be 1 hour, right? So I'm going to have to divide, and I get 454.54 miles. So I go 454.54 miles per hour. So with the speed of the plane against the wind, I was able to go 454.54 miles per hour, right? mph. Then on the way home, or on the way back to Cleveland, it's still 2,000 miles, right? The distance hasn't changed, but now I'm doing it in 4 hours. So what's my speed there? So that's 500 miles per hour. So on the way back, you get to go 500 miles per hour. And I want to know specifically what is the speed of the plane and what is the speed of the wind. Well, I was able to set up a system of equations that already eliminates, so I can just add these suckers together. My w's eliminate, and I get 2a is equal to 954.54. So A, definitely running out of room. A is equal to 477.273 miles per hour. So that's how fast the plane goes. No matter what, right? No matter what the wind is doing, that's the speed of the plane. Once I know that, then I just plug it into one of these guys. And I think you can do that on your own because I'm definitely running out of space. And I get that the speed of the wind is 22.727 miles per hour. So the plane is going the same speed no matter what, but when it's going against the wind, it's going less than 474 miles an hour. And then when it's going with the wind, it's going faster than, 477 miles per hour. So hopefully that makes sense how we kind of use that. If you guys have any questions at all, make sure that you reach out and we'll do some practice of this and we'll see you guys in the next video.